corrected audio. A lot of you I don't recognize, which is great. If you are interested in this intelligent and interactive systems seminar more generally, you can send me an email to list@visanglia.edu. You'll get the announcements. I haven't been spamming the whole school, so I just found this list instead. So anyway, our speaker today is a PhD student who works with Ken Chan, and the way you wrote your research interests were so poetic that I wrote them down. So I'm going to read this. This sounds almost beautiful. So he's researching the ways in which programming language design can help us write machine learning applications that are painless to compose, easier to reason about, and safer to use. And this is something I think a lot of us in machine learning wish that we had. Right. So I'm really looking forward to hearing about your work.
Right. So thanks, Professor, for that introduction. Right, so I think a lot of us here are interested in machine learning as a field. I am also interested in the field. People are interested for different reasons. Personally, I like the idea of letting computers or machines assist humans in tasks that humans can probably perform, but it's probably expensive, for whatever definition of expensive for humans to do it on their own. And I'm also in kind of parallel very interested in programming language research. And I think a lot of programming languages research has very similar philosophy of letting the machine or letting the computer assist the human. In this case, the programmer, seeks assistance in writing better programs for whatever definition of better programs. Maybe the programs are less buggy, or they're more extensible, or they are more optimized, they are faster to run, or easier to understand. So a lot of programming languages research focuses on how the runtime system or the programming language can help the programmer automatically write such programs. And in this talk, I kind of hope that I can appeal to that same sense of assisting machines assisting humans in prediction tasks, and sort of apply the same philosophy to the machine learning programmer, applying that same philosophy to how they write their code, and letting the computer or the machine assist them in writing code that is then going to do prediction tasks. So again, I think machine learning has a lot of definitions, but I think generally all definitions seem to be motivated by prediction or discovering some sort of pattern or label or anything like that. So I kind of just Googled machine learning in Google Images, and I think some of you might recognize this image, especially if, due to the popularity of this library. And I think this sort of image corroborates my vague theory that a lot of machine learning work, the first question is, what are you predicting? For example, the very first few nodes talk about what do you want to predict, a category or quantity, or do you want to regress or classify? So in this talk, I'm actually going to not talk about how to solve this problem for all of machine learning, how to make every machine learning program better ever, no matter how poetic that sounds, and even if that's the kind of eventual research goal. I'm going to talk about a very restricted, I guess, set of machine learning tasks, and the set of path I'm looking at is when you want to predict, a category of labeled data, like say you want to use naive Bayes to classify documents. So that's the sort of running example I'm going to go with in this talk. And again, the idea is I'm going to try and sort of describe what I think is today the process for going about this task. And in that description, I hope I can sort of show recurring themes about how we can improve that workflow or that process. So I said predicting a lot, so let's just talk about the specific example that we're going to talk about in this talk about today. So topic models, basically the idea is that you have at hand a bunch of documents and you know what their topics are. Topics could be binary, it could be like spam classification. Is your document, is your email spam or not? Or it could be not just binary, you could have a bunch of news sources and you want to categorize them into like sports or politics or entertainment or what have you. So the idea is that you have a bunch of labeled documents, and how can you use these labeled documents to predict the label or the topic of a new document on tomorrow or whenever. So I like to think of this as two processes, and some people don't, but the first process is that how do you use the label documents to sort of build your knowledge of what it means, what this correlation between topics and documents is. And then the second part is actually predicting, like using that knowledge that you built from whatever data you have, how do you use that to predict? So, I mean, I might go and ask somebody, because I'm not an expert in like linguistics or how documents and topics are correlated, so I might ask what's a good model to begin with if I just want to start with a model that's already in the literature. And somebody might point me to naive Bayes, which already has a lot of words that I haven't defined today, and I am going to try to define them briefly. So the basic idea with naive Bayes is that each topic provides a certain distribution over words. So spam means there's a certain distribution over words. Some words might occur more when the topic is spam than when the topic is not spam. And that each distribution I'm specifying is beta over here. So the topics are labeled by Z. So for each topic, I have a certain distribution over words. And where does this distribution come from? Like maybe I have a lot of knowledge about the world and I know what this distribution over words looks like for each document. Then I could just hard code the distribution over here. And if I don't, I can use a Dirichlet prior, which is what this model is doing, to sort of have an uninformative way of randomly sampling distributions over words. So that's what this prior is doing over here. And similarly, I could randomly sample a topic for each document. And the idea is that I'm generating documents here to see what documents look like when I sample topics for them. So okay, so this is a model that's like kind of well studied in the literature, and I have two questions, say, if I want to use this to do my prediction task that I mentioned before. So my first question is, I have labeled documents. How can I take advantage of those labeled documents? If I'm already using this model, how can this model be better updated with the actual data that I have? And the other question is, how do we actually do the prediction? Like, how do we go from this model and the label documents to predicting the topic of a new document? How do I do that? So I might talk to a machine learning or like a statistics person, and they might say, well, this model was built this way for a reason. You're using Dirichlet's and categoricals for a reason, and the reasons are conjugacies. And conjugacies mean like a lot of terms will cancel out, and you could do Gibbs sampling. And what does that mean? I say, okay, so let's read about what Gibbs sampling does. And I open up, say, a paper on like Gibbs sampling by Resnick and Hardisty, and specifically Gibbs sampling for this model, for this particular naive Bayes model. And the general Gibbs sampling algorithm is this. It doesn't matter what it is, but the point is that in this nested loop, we have this distribution that we want to sample from. And this is kind of written in a general form. It's not written in terms of this model. So our question is, if we want to use Gibbs sampling for this model, like, how do I find this distribution for my model? And not only that, can I sample from it for each data point? So it looks something like this. So how do we actually sample from this? Well, thankfully, this paper actually, for our particular model, lays out the steps and derives a Gibbs sampler for us, step by step, equationally. So the notation has changed a little bit, but it doesn't matter. So the point here I'm trying to make is that there are many steps that we go actually around 21 steps or so in deriving an efficient Gibbs sampler for this particular model. And it involves a lot of symbolic math that is, at the end of the day, kind of mechanical or kind of straightforward if you follow the rules. But in many times, it's a lot of work. Like, you have to know which steps to apply. You have to know that there are conjugacies here that I mentioned earlier that help these factors cancel out. For example, it's the conjugacies that actually make this tractable sampler. So, okay, great. So I was lucky. I mean, I have a paper that lays out the steps for me, or I know how to do, I know the theory behind conjugacies, and I can derive a Gibbs sampler. Now, how do I actually put this into code? So all this was in paper, right? So I did all this math, and I derived the formula for the conditional distribution. That's what I did on math, on paper. How can I actually put this into an algorithm? Well, in pseudocode, the algorithm might look like this. It's very specific to the model that we've spoken about, to the naive Bayes model. There are a lot of words here, like, you know, assign a new label as described in this section, or, you know, subtract word counts from this word count from whatever class. You know, it's very specific to this particular model. But you know what? It is a Gibbs sampler. It even takes advantage of the label documents that I have, and it's derived for me. Now, what if I want to change the model a little bit? So the conceptual change here is very small. What I've done is I can show you previously. What I've basically done is remove this plate diagram one step above. So I'm allowing, earlier I decided that each document has one topic. And now I'm saying that I'm actually allowing a mixture of topics from word to word. And this is an idea that was introduced in an original paper on the latent Dirichlet allocation paper. So conceptually, most of this model is the same. The only difference is that I'm sampling this for each document. Well, the question remains the same. How do I perform inference? How do I take advantage of the labeled documents that I have? The model has changed a little bit. Does that mean the inference has to change a lot or a little bit? I'm not sure. So again, thankfully, Heinrich has a paper to show how we can do Gibbs sampling for LDA. And I say thankfully because, I mean, it might be clear to many people that Gibbs sampling is possible because the conjugacies still remain. But for many others who are, say, new to the field or aren't aware of the conjugacies, for example, deriving these steps is no mean task. And it's actually not surprising that most papers don't actually specify how they derive their Gibbs sampling algorithm or any algorithm, for example, let alone show pseudocode for their sampler. But you know, in this case, I'm lucky. I have pseudocode for this model, Gibbs sampling this model. Great. So all I have to do is read this paper by Heinrich in 2005 to understand what, say, Heinrich might mean by equation 79 and things like that. And specifically, I can do Gibbs sampling for the LDA model if I understand this paper. And it's basically like these papers are documentation in some sense, a very extensive documentation for the particular sampler that they wrote. And not many such documentations exist. People don't actually write the sampler. Okay. So great. So is Gibbs sampling the only thing? No. What if I want to try the variational EM algorithm that was described in the original David Bly paper? It's the same model, but I'm changing the inference algorithm a little bit. Earlier, I kept the inference algorithm the same, but I changed the model. Here, I'm doing the reverse. So for LDA, can I apply a different inference algorithm? Sure, I'm really lucky today. So there's still an algorithm specified for doing variational inference over LDA. Great, I just have to understand what this paper means about specific notations and how it maps over to my model, and I'm good to go. So far, like, we've seen two models and like two types of inferences. What if I change the model yet again a little bit? This is also specified in a paper. This is a new model. The difference here is that instead of using a Dirichlet over the topics, I'm doing a logistic normal. Again, just like kind of a one-line change in the model, right? And maybe some conjugacies apply, maybe they don't, I don't know. Maybe I'm repeating myself here, I don't know. But I don't know, actually. I haven't researched the literature to see if Gibbs sampling works for this model or variational EM. It probably isn't. The search itself probably wouldn't take time, but it might take me a lot more time to actually sit down and read those papers and understand how to write the sampler. So this is sort of like a pattern that, you know, if we're programming in any other like sort of domain, we might quickly see that this is a lack of abstraction that's kind of happening here, and we want to abstract the concepts in some way. And if we have a small conceptual change, we also kind of want a proportional change in the code. We don't want to have to write a new inference method or a sampler from scratch. I mean, it might help us. It might help us get publications, for example, because it happens to be that every new inference sampler can be published because it's such a monumental task to actually do it by hand. But it needn't be so. I think machines can help us sort of figure out some of these details. So this is how I understand the workflow is today. This slide is sort of supposed to be, I don't know, open a discussion later. But I think I've made the same points earlier. Like, how does it actually work today? I guess here I'm kind of basically asking for the cost-benefit analysis between putting a lot of money into hiring grad students who can then read the papers and do this work, versus maybe putting money into developing automated systems in whatever way possible for us to do this for us. So I think if there's any, like, again, one word that I want to be the takeaway of this talk, I guess it's modularity, which is basically we want to be able to reuse different components of our system. So in this case, the examples that I showed, sometimes I wanted to use the same model over different inference methods or vice versa, and I want to separate out the two components for whichever model, whichever inference. In this specific case, I'm talking about generative models and specific types of inferences. So this is not a new idea. Decoupling is not a new idea at all. Like, I think it first started with compilers many, many years ago, and it has protected us, quote unquote, from having to write machine code for so many years. We write in high-level programs. These days, software-defined networking is another successful example of abstraction, where programmers don't have to write program routers, network routers. They can write in high-level languages, and the routers understand their instructions. So what does such an abstraction entail for machine learning? And this has kind of been a question of late. Like, we have a mathematical language of statistics, and then it is enhanced with machine learning concepts, right? Like Gibbs, or expectation maximization, or variational. And we have plate and tilde notation, and I'm able to use this language to sort of express or communicate conceptual delta changes or ideas, and how can we make this language sort of executable? That's the kind of goal. And this idea was started, has another name, I guess, and that's like probabilistic programming systems. And the main result from probabilistic programming research has been to try to decouple models from inference. So I might sometimes say model and sometimes say generative story, and that's why this is a sort of, this talk is restricted to a certain area of machine learning where you are able to write generative stories for your model. And the focus of this talk is going to be mostly about how to compose different models, specifically in a language that is being developed in Indiana. I'll briefly mention how it also allows us to compose inference, but that's going to be the subject of a talk in 2 weeks by Rob. So before I get to Hakaru, I guess I have a list of, I basically just wanted to say that it was cool that the gravitational paper, Waves paper, actually used a probabilistic programming language. I haven't looked at the actual way they used it or the code that they wrote for it, but it's kind of nice to see it being used in real life. Of course, This is not, Stan is a language being developed in other universities, Columbia and NYU, stuff like that. All right. So I repeated this. Great. So what are generative stories, right? Executable versions of tilde notation. So let's look at a simple example in what's currently called concrete Hakaru. Hakaru is the name of the probabilistic programming language that I will be using for the rest of the talk. So in this case, we see basically a medical model that I think has been a simplified version of which has been shown like in many intro classes. The idea is that the final return value, a cough is something that we observe, we might have data about, and we're trying to infer what does it mean about my having a cold or my having lung cancer. And the generative story here is that independently in the world, my chance of having lung cancer is a Bernoulli distribution over 0.01, which is a coin that comes heads 1 out of 100 times. And independently in the world, I have this much chance of getting a cold, and I have a direct deterministic relationship or likelihood of having a cough dependent on the two priors. So in this case, I wanted to point out this type, right? So what is this measure? So a measure is a distribution. It's an unnormalized distribution. And a probability measure is a normalized distribution. And the reason that this language deals with unnormalized distributions rather than normalized ones is that sometimes we can get away with not having to normalize your distribution, which can be an expensive procedure. So sometimes the fact that it's not normalized doesn't matter. And by normalized, I mean the probabilities don't have to add up to 1. So here the type is that medical is basically a function. I can think of every term in my language as a function. And in this case, medical is a function that takes no arguments and returns a measure over Booleans, meaning to say that if it's a measure, I can sample from it. So if I sample from this function many times, I'm going to get different Booleans, sometimes true, sometimes false. And that Boolean basically represents whether I coughed or not. And each time I'm sampling from this measure, I am sampling whether I have cancer or not. I am sampling whether I have a cold or not, and then I'm deciding whether I'm coughing based on the two things. But really, I'm never going to get true for cough unless I sample true for either cancer or a cold. So that's what this measure is supposed to represent. And I already specified what burn means. Burn is again a function, like I specified, like it's a function from given a probability, it goes to a measure over Booleans. Great, so what is the difference between this symbol, which I'm going to call it tilde, and equal sign? So basically, tilde can be thought of as actually sampling from a distribution. Tilde doesn't, in types, make sense unless you have a measure on the right-hand side of tilde. So in this example, cold, are there any guesses for what cold might have, what the types of cold might be, say, in this example?
Could it be a probability distribution?
In here?
Yeah.
No. Is there any other guesses? Unfortunately, no. Right, so it's a Boolean. So the type is a Boolean. That's right. And any guesses about what the type of cold might be in this example? Right, so it's a measure over Booleans. Because in other words, I applied burn to a probability, I get a measure over Booleans. And I'm just equating what I got to cold, rather than sampling from it. So that's sort of a semantic, high-level description of the difference between, say, sample bindings versus just variable bindings with a let. So let's see.
For example, bear.
So so burn will output whether either true or false.
Okay.
Yeah. So booleans are represented by two symbols, true or false. So it represents something of this type, of type boolean.
With that probability.
Yeah, with that probability. Yes. Thanks. Great. So at this point, I'm going to jump straight to the naive Bayes model in this language. So on the right-hand side, I have still the tilde notation from before and the plate notation from before. And for those unfamiliar with plate notation, I'm just going to quickly say that a box with a z means you loop whatever's inside z times. It's essentially a loop. And I'll explain that more later. But here we have the same naive Bayes model as before in code, in executable form, in this probabilistic programming language. So let's jump to one part of this code first. And I've shown this code here and sort of hidden the rest of it. And I want to show the sort of similarity between what's happening here and, say, the line for beta, theta, and zetas in the tilde notation. And the idea is that each of these for eaches have been converted to a plate, because each of these for eaches is a loop, and the notation of plate here has been used for the keyword plate over there. So let's talk about more details. So what is Dirichlet, right? So Dirichlet is a distribution or a measure only when given an array. So Dirichlet has that type. It's a function from arrays to a measure. So in this case, I'm taking this function Dirichlet, I'm passing it an array. In this case, it's an array of w ones. It's all ones, w times. W is a number. And I'm passing this array to Dirichlet. And that's fine. So what is theta? So in this case, theta is sampled from a Dirichlet over this array. So the type of theta must basically be this Dirichlet, when it's passed this array, Dirichlet passed an array becomes a measure. And when I sample from this measure, I get an array of probs. And that's what this theta becomes. It's an array of probs that I sampled from this measure. And similarly, categorical. Categorical is something that takes theta. So it takes actually as input an array of probs. That's what theta was. And it returns a measure over natural numbers. And that represents the categorical distribution. What does this mean in like sort of in an intuitive sense? The categorical distribution is basically you give it a list of probabilities. Say I give it the probabilities 0.1, 0.3, and 0.5. Then when I sample from this distribution, I will get the natural number 0 with probability 0.1, the natural number 1 with probability 0.2, or whatever I said was the second one, and 2 with probability 0.5. So it basically is a distribution over the natural numbers. So the specific weights that you apply to each natural number is what you pass in as the input to categorical.
Can I ask a
Yeah.
couple of pretty obvious questions? I just want to make sure. So W and Z in your source code are scalars specifying how many possible words or topics or whatever there are, whereas W and Z on the right side are random variables, right?
No. So maybe I should be more specific about this. So let's look at this code again. So W is a number. It's 100, for example. Right. And in this code also, this is just a size. How many times do I want to loop this?
But on the right in the plate, W is referring to
That's right. That's right. So this, yeah, this,
okay.
yeah, I call this W a doc, for example. Yeah, yeah.
And then
Right.
another obvious question, but I think you probably sort of what I just understood. Burn was referring to earlier.
Yes.
Okay.
Yeah. Right. Okay, so it's okay even if a lot of these things don't make sense. The takeaway again is that we've managed, we're talking about specifying the model as honestly as possible in code. So what does plate mean? I wanted to quickly talk about this plate notation. And here this plate notation is talking about the loop over betas specified by this line over here. So it's saying that z times I am going to sample from this Dirichlet. And it's a Dirichlet because that's what the model specified up over here. For each label z, I am sampling a particular distribution from the Dirichlet distribution. Similarly for zetas, I have another plate, a for loop basically, d times. For each document, I'm sampling a particular topic. So this is sort of like a cleaner way of specifying, at least in the machine learning language that we might be used to, like what we're trying to do. So more generally, the type of this keyword plate something of something might have the following form. And I'm saying that this is sort of like a functional binding. So this is a variable that can be used inside the body here. In this situation, actually in the code, I'm not using that variable at all. So I just decided to give it the name underscore. But I will show examples later, or maybe one, where that variable index is actually used. But the idea is that, again, plate, the body of plate is basically a measure that you want to sample from repeatedly. Beta is drawn from a measure. W, Z, anything inside a plate notation is repeatedly being drawn. So its type is actually a measure. And as long as you give it a measure, it'll repeatedly draw from this measure and collect the items into an array after it's done. And that's what plate is doing here. So that's what we've seen so far in the naive Bayes example. This is similar. So for the docs, there's a nested loop. So the first loop is over the number of documents. And for each document, I'm sampling n words, where n is the length of the document. So in this case, for each document I actually have to find out what its length is and then sample it that many times. So here's an example of where that I is actually used in the for loop. So I'm going into excruciating detail here about how to specify kind of a non-trivial model in this language. But the key thing, again, I wanted to show by showing so much detail is that, this is it. We don't have to go further than this, firstly. I mean, that's the ideal. And secondly, if we want to change the model, we don't have to change that much in this code. If we wanted to go from naive Bayes to LDA, the one change that we made, firstly, which was, I'm going to go back here for a second. So this theta here is static, right? There's just one theta that we draw from Dirichlet. But if we go here, we're actually doing it for each D. So that's fine. So that's one change we made here already. We're doing plate. And the second thing is now we're drawing a topic for each word. And that's why zetas, which is the topic, which initially was just one over the whole document, is now, it has this nested loop. And we can see that over here, zeta is now happening n times d times. So it's nice to be able to actually also executably say that this is a change in my model, but I want to apply the same inference technique or a different one. And a lot of this code that I'm showing right now, I have to I have to put a disclaimer that this is still what is currently called pseudo hakaru. And a lot of these functionalities, for example, plate over certain types of variables are still under progress. It's still being developed. But I wanted to kind of show the motivation behind what our research is doing. So let's see. The key idea here, if you ignore the fact that I forgot to change this to LDA and this to LDA, the types of LDA and naive Bayes are the same. The type of naive Bayes is basically a measure over pairs of documents and labels. And the type of LDA is also a measure over pairs of documents and labels. And that allows us to use each of these models interchangeably in whatever inference technique we might want to use. And you can imagine, I haven't shown this today, but I showed this transformation, but you can imagine going from LDA to LDA logistic normal is similarly small. But imagine that like you want to not just do document classification. Tomorrow, once you've developed your document classifier model, you want to go on to bigger and better things, and you want to use a document classifier in something bigger. This is an example I just came up with briefly with talking to Ken, but the idea is the same. Once you have a way of getting the topics from a model, maybe you want to predict something else. Like you want to take documents from tweets, and using the topic of the tweet, you want to see whether there's a lot of flu or it's just one person who's talking about a flu. And the idea is that because the types of the two models are the same, it's very easy to just switch whatever model you want into your classifier. And there are more pseudo-Hakaru examples and Hakaru examples of generative stories, which I'm not going to talk about today, but maybe I should make a website or something. Anyway, so the first part of the talk, the decoupling, was models, and I showed a few examples of how to write models. The second part of the talk is basically how to, second part of the research is how to kind of implement actual inference methods abstractly over these models. And one key idea here, before I sort of like, I'm nearing the end of the talk here, just like, and before I close up, I wanted to say that the key idea is that you can always forward sample the model because you have a joint distribution, and then you can reject the samples that don't match your data. But that's only the first step, and there are more general tools like disintegration or simplification that help you do approximate and exact inference that are provided by the language. This is sort of the approach that Hakaru, the probabilistic programming language that I showed today, has been taking. There are sort of other approaches taken by the languages that I've mentioned earlier that are used in the real world, like STAN or Picture. But the basic idea is still the same. You have a generative model, and you want to condition on specific variables inside the model. So I'm not going to go into details about this today, unfortunately, and this is something that will probably be tackled by Rob in a couple of weeks. But I kind of wanted to finish up by saying, currently today, like the models that do work, for example, even with naive Bayes, if you assume that you have a binary label, so that instead of Dirichlet categorical, you're using conjugacies between Beta and Bernoulli, and some simpler models like a linear dynamic and burglary alarm. And I'm going to wrap up here for any questions or anything like that. Yeah. So at the very core, yes, because I mean it's developed in a functional programming language. It is also aiming to be a functional programming language in its semantics, and the host language is based on lambda calculus. So yeah.
Could you say something about related performance of because in general the more abstract
Right, right. So yeah, ideally I would talk more about that. So let's see. So um, in these two examples, actually, we do not lose any performance, and we gain a whole lot of modularity. In this example as well, when Gibbs works, we basically achieve the performance of Gibbs, of a handwritten Gibbs sampler. But in many cases, as the models get more and more complicated, we can't do the same inference techniques like Gibbs yet. Like more complicated, like instead of 2 labels, if you have more labels, right now we can't do Gibbs, and we have to fall back to much slower inference techniques right now. So for it, like there are a few models for which we are on par with handwritten efficient inference techniques, and these are the types of models that we work for that, basically.
Are there ways to specify which inference you're using? So like, if you wanted to manually configure a Gibbs sampler to a
Yeah.
relational just to do comparative benchmarks.
Right. So yes. So in the specific case, like between Gibbs and variational, since variational is not implemented, you can't choose variational, but you can say choose between Metropolis Hastings or Gibbs if you know that for your model, Gibbs is something that is actually tractable. And the way to choose it is very simple. You just specify, I want to use Gibbs versus I want to use Metropolis Hastings. Yeah, there's like syntax. But again, a lot of this stuff is still under development. So like today, if your mod, it's so many moving parts. So if you just change the model a little bit, it might not work. But yeah, the goal is, yeah, you should be able to plug and play any. Yeah.
Can it be applied on non-statistical tools like neural networks or others?
So I don't know too much about neural networks. I don't know who to talk to about that, and so we haven't really thought about it.
I think fundamentally Hakaru is for describing probability distribution. To some sense, you can do neural nets because you
Like
can describe neural nets
Bayesian.
through a Bayesian neural net
Yeah.
describing.
Yeah.
And in that case, yeah, Hakaru today can
Right.
represent that.
But yeah, I'm not sure what type of neural nets you're looking for. Like I don't know.
Not the specific type. For example, in my perspective, neural networks are not formalized with the statistical formulation that we have. That I mean that can you apply these techniques on the non-statistical models like neural network, for example, multi-layer perceptron, for example.
I think as far as I understand it, you have to be able to specify a model in like, I think what you're calling a statistical way, I'm calling a Bayesian or probabilistic generative style. And I think if there's an interpretation of your model in that style, then I think then I can think of how to use the system for it.
Just as a comment on that, I think at least in vision machine learning, along with the sort of sub-communities, they're trying to understand the relationship between Bayesian networks and probabilistic models in general and neural nets, because there's certainly at some level of abstraction, they're somehow related. And I don't think anyone really can say right at this moment what that relation is, but it sounds like maybe you could sort of fit it into this framework if you shoehorned it in, but that
Something like regression or something.
Well, you can shoehorn it in, and then you can, part of the thing that Praveen hinted at is that you can kind of write your own inference method.
Right.
And then you would essentially write a specialized inference method that does back propagation. That only really works if you put this model in, but will probably be something weird if you put something that doesn't represent a
It
neural
might
net.
do something, who knows?
Right.
So I have sort of more conceptual question, which is that, so I don't know very much about programming languages, but my understanding is that compilers try to do these transformations in programming on the programs that I write that optimize the running time or optimize for other things, but primarily maybe for running time. And the point of
Yeah.
can't answer that.
Yeah.
Now, it seems in this case, you're not trying to or even able to guarantee that because these different inference algorithms make different assumptions. They're all approximate inference algorithms, for instance. So Gibbs sampling, for instance, has a bunch of parameters underlying it, like what the warm-up period is and how many samples you draw and stuff like that. So is the idea that the language will somehow decide those parameters for me, or will I provide hints, or like how do you sort of, it seems like not only is it trying to choose the inference algorithm that potentially fastest or most efficient, but also the one that might give me the best answer for certain distributions. It seems like
Okay.
a whole orthogonal.
Okay, so I'm going to try to break apart that question.
Okay.
So going backwards, I think there was something you said about the language choosing the inference algorithm for you. And so far, I think the philosophy has been like, give as much control about the inference technique to the user. So the language isn't choosing the inference technique necessarily. So say you have chosen Gibbs. I think it is a hard task to try to prove the correctness of Gibbs. The only way we can prove that we are doing Gibbs and not something else is that our encoding, say, of the Gibbs transformation is a direct translation of the textbook encoding. We're not doing anything else.
Right.
So as long as the textbook encoding of Gibbs is sort of like proven mathematically or using asymptotic proofs or like Metropolis Hastings or whatever, and our encoding is basically the same translation. We're not doing some extra memoization of terms or anything like that. Then like sort of we rely on that translation. But there's something earlier you mentioned about like a lot of programming language research, like trying to prove that transformations are correct. And we do, I think we are capable of proving certain transformations correct, and that is definitely like our goal. And the transformations are basically the ones that are more exact, where we're not actually doing any sampling yet. We're just taking one program and producing another program in the same language. So algebraic simplification is one example. And sometimes exact inference falls out of algebraic simplification, meaning hidden variables might get integrated out, for example, and you might have variable elimination. And to prove that the transformation we're doing there is keeping the semantics of the program the same, it might run faster, but it's still the same measure. We rely on measure theoretical semantics, basically.
Right. Okay.
Yeah.
So I guess the answer is that there's certain transformations that you would do that are, for instance, algebraic that are guaranteed, like they're easy to prove.
Right. Right.
One can prove that they're not changing your original problem.
Right.
But then there's this other issue about which inference algorithm you use. Because, for instance, Gibbs sampling is an approximate inference algorithm. So even if you exactly implemented like this in a paper, you still might not get the right answer under certain circumstances. There's going to be some error bounds and stuff. And I think what you're saying there is that you give the programmer
for now,
control
maybe.
It's worth clarifying. The semantics of all these approximate inference algorithms is uniquely defined for every model that's given. So it's unique for every, so the pair of the model you give it and the inference does specify a unique approximate model.
Right.
And that is something that I think we're close to, or like in the process of showing that that it does for any model. This particular inference gives the correct approximate.
Right. Okay. And it's up to me as a programmer to decide potentially which of the approximate inference algorithm I want to use. So it's like my fault if there's
Well,
error.
so the other approach. So on the other hand, like Stan, for example, the programming language Stan. So they sort of have they apply the same inference technique to any model you write in their language. If I understand this correctly, the Hamiltonian Monte Carlo. Few. Okay, but they have a few, and I think they choose like what seems more appropriate. You might give some hints using language keywords, but there's sort of a distinction. They restrict the model language so that you can't so that inference technique is easily applicable. So over there they trade off modularity a little bit, but then you do get better performance because those inference techniques might be very highly optimized for those models. And I think over there they have a greater responsibility of proving that whatever transformation they're doing, whatever inference algorithm they're doing there is kind of like asymptotically correct. Yeah.
I'll just ask one more question.
Yeah.
So in terms of, maybe you just sort of answered this, but in terms of connections to existing work like SAM, which I know nothing at all about,
Yeah.
I can completely lie and completely whatever, but is what you're trying to do here sort of, should I think of it as like a generalization? Like you just mentioned that SAM only is restricted to certain kinds of problems, so is this more general in terms of the models it can represent, or is this sort of like a specific strength or something here?
I mean, in some sense, it can represent more models, but then it works for fewer of them. So I don't know if it's yet a generalization of Stan. Stan certainly seems to work on just a pure number more models than, say, our system does.
Right.
But in theory, I think since we're also we're providing blocks for the user to build whatever inference method they want, and like the modeling language is also kind of more general purpose. Yeah, you might say that in theory, we kind of tackle a broader class of problems.
Okay.
Yeah.